This is how I'd use the simulation to explain why power depends on both current and potential difference, and how to use the simulation's special power meter to measure how quickly energy is shifted in the bulb. I'd probably introduce the topic by saying something like, in our simulation, the expanding red energy circle shows how quickly energy is spreading out into the environment. If the energy is spreading out quickly, then the bulb is bright. If it's spreading out slowly, then the bulb is dim. How quickly energy is shifted is called power. High power means shifted quickly. Let's keep the bulb resistance constant. In practice, this just means we use the same bulb. And let's try and understand why increasing the voltage increases the power. If I increase the battery voltage, what happens to the amount of energy each charge loses as it goes through the bulb? Each charge loses more energy. And what happens to how quickly charges with energy arrive at the bulb? Charges with energy arrive quicker. So, does the power depend on just the current, just the potential difference, or both current and potential difference? The power depends on both the current through the bulb and the potential difference across it. In fact, the power in watts is just the current in amperes times the potential difference in volts. Let's add in an ammeter to measure the current through the bulb and a voltmeter to measure the potential difference across the bulb. We'll also add in the simulation's special power meter, which doesn't really exist in real life, to measure the power of the bulb. If the PD is 3 volts and the current is 0.5 amperes, then the power is 3 times 0.5, which is 1.5 watts. If I increase the PD to 6 volts, then the current increases to 1 ampere and the power is 6 times 1, which is 6 watts. And if I increase the PD again to 12 volts, then the current increases to 2 amperes and the power is 12 times 2, which is 24 watts. Notice that doubling the battery voltage from 6 volts to 12 volts doesn't double the power. It quadruples it from 6 watts to 24 watts. And that's because doubling the battery voltage doubles both the potential difference across the bulb and the current through it. To make the numbers easier, the simulation behaves as if the bulb obeys Ohm's law. Doubling PD doubles current, but this is definitely not the case with real filament bulbs. They are very non-ohmic. What about keeping the battery voltage constant and changing the resistance of the bulb? This is what happens at home. The mains voltage is constant and we use bulbs of different power ratings. The bulbs have different power ratings because their resistances are different. I'm going to double the resistance of the bulb from 6 ohms to 12 ohms and keep the battery voltage the same at 6 volts. What happens to the PD across the bulb? it stays the same, 6 volts, because power supplies are constant voltage providers. What happens to the current through the bulb? That halves from 1 ampere to 0.5 amperes. So what happens to the power? That halves too, from 6 watts to 3 watts. If the bulb is half as bright, then the battery is working half as hard. This confirms again that high resistances cause power supplies to work less hard, not harder. The higher the resistance, the dimmer the bulb, and the lower your electricity bill.